You know, from the bridge you drive over every day to the plane you fly in, we are constantly betting our lives on the materials that build our world. We trust them. And why? Because they've been tested, right? Rigorously. But what if those tests, as precise as they are, don't tell the whole story? What if they're hiding something? That's what we're going to dig into today.
Okay, so let's start where everything should be perfect, the lab. We're talking about a world of controlled conditions. We take these pristine, flawless samples of material, we stick them in these high-tech machines, and we meticulously pull them apart. The whole point is to get clean, reliable numbers about a material's fundamental strengths.
And then you get this, a real-world disaster. A structure built with materials that passed every single test with flying colors just fails, catastrophically. So this right here, this is the conflict, isn't it? The clean, tidy lab versus the chaotic, messy real world. So what gives? What are the tests not seeing?
To solve this mystery, we've got to go back to the basics. Let's first really understand what these lab tests promise us and why they are, for sure, the bedrock of all modern engineering.
So, the most classic test of them all is the tensile test. Just imagine stretching a rubber band until it snaps. We're basically doing the same thing, but with a metal rod, and we're measuring the force it takes. Now, to make sure we're comparing apples to apples between different materials, we calculate something called engineering stress. It's really just the force divided by the original size of the sample. It creates a universal language for strength.
And what's amazing is that this one simple test tells you a whole bunch about a material's personality. We learn its stiffness, how much it resists being stretched. We find its yield strength. That's the point of no return where it's permanently deformed. We find its ultimate tensile strength, the absolute maximum it can handle before it starts to fail. And we see its ductility, basically how much it can stretch before it finally breaks.
And all of this data creates this perfect, predictable curve on a graph. It's a kind of certainty that engineers love. It lets them design everything from massive skyscrapers to something as simple as a paperclip. This is the beautiful, clean promise of the lab.
But what happens when this perfect world of numbers slams head-on into harsh reality? Well, let's look at one of the most famous and tragic stories in the history of engineering.
Meet the Liberty ships. These were the workhorses for the Allied forces during World War II. They were built fast, using steel that, on paper, passed all the tests for strength and flexibility. But out on the cold seas, some of them just snapped in half, with almost no warning. The steel that was supposed to bend, instead, shattered like glass.
And this brings us to the billion-dollar question. I mean, the engineers had the data. The steel passed the lab tests. So why did the ships break? If our methods are so good, why do these kinds of disasters still happen?
The answer, it turns out, is hiding in the gaps. The gaps between the perfect little story the lab tells us and the messy, complicated novel that it's the real world. So let's break down exactly what those gaps are.
First off, let's talk about force. In the lab, we pull on that sample in one clean, straight line. Simple. But think about a bridge in the real world. It's getting hit by wind from the side, by the weight of traffic from above, and it's dealing with constant vibrations from below. The forces out there are a chaotic, unpredictable dance, not a simple, straight pull. Next, let's look at the material itself. The samples we test in the lab are perfect, tiny, polished little jewels. But real-world parts? They have tiny scratches, hidden stresses left over from when they were welded, and microscopic flaws from manufacturing. And here's the kicker. Failure almost always starts right there at one of those tiny, overlooked imperfections. And then there's the third huge gap, the environment. Lab tests happen in a nice, comfy, climate-controlled room. But a real part on a car or a building is out there fighting rain, salt, humidity, corrosive chemicals, and brutal swings in temperature. And this is where things can get really wild. This brings us right back to those Liberty ships. This graph shows something absolutely critical about steel called the ductile to brittle transition. See, at room temperature, it's tough and it'll bend. But if you get it cold enough, its whole personality changes. It becomes as brittle as an icicle. And that's what happened. The icy waters of the North Atlantic were the fatal blow, turning that strong steel into fragile glass. And finally, there's the silent killer, fatigue. You see, most things don't break from one giant single impact. They fail from a death of 1,000 cuts, or millions of them. Tiny, repeated stresses over and over again. The best analogy is the paperclip. You don't break it on the first bend. You bend it back and forth, and then pop, it snaps. That's fatigue, and it accounts for the vast majority of failures out there. Okay, so after all that, you might be thinking these lab tests are totally useless, but they're not at all. In this last section, let's look at how good engineers take this imperfect data and turn it into the wisdom that keeps our world standing. This is really where the science becomes an art.
So here's the real secret. Smart engineers know not to treat lab results as an absolute prediction of the future. They use them as a measuring stick. Is this new batch of steel as good as the last one? Is this new aluminum alloy better than the old one? It's all about comparison and quality control, not fortune-telling.
And even for quality control, the numbers are never perfect. Just look at this table. These are test results from 2 different batches of the exact same steel. And as you can see, the results are kind of all over the place. This is what we call scatter, and it's just the natural variation you find in any material.
This leads to a huge takeaway. A material's strength isn't just one single number you can look up in a textbook. It's a range, a statistical probability. So a great engineer doesn't design for the average strength. They have to design for the weakest possible case, for the outliers, for all the what-ifs. So how on earth do they do that? Well, they use a clever concept called a factor of safety. It's pretty simple, actually. They do all the math to figure out how strong a part needs to be, and then they make it way stronger. Sometimes 2, 3, or even 10 times stronger. This big margin is their safety net that accounts for all the uncertainties we've been talking about. And check out this quote, because it really flips the whole problem on its head. It basically says that 90% of the time when something breaks, it's not actually the material's fault. It's a flaw in the design. A sharp corner that concentrates stress, a bad weld. Those are the real culprits. It tells us that how you use a material is often way more important than the material itself.
All right, let's bring it all home. What should you take away from all this? First, lab tests are absolutely essential, but they're a ruler, not a crystal ball. Second, the real world is messy. The forces, the environment, the hidden flaws all matter. Third, a material's properties aren't one fixed number. They're a range. And finally, good engineering, great engineering, is really the art of managing all of these uncertainties with skill and a healthy dose of humility.
You know, in the end, lab tests give us a language, a vocabulary to talk about materials. But the real skill, the poetry of engineering, is in how that language is used to design and build things for a world that is never, ever perfect. So the next time you cross a bridge or look up at a tall building, maybe look a little closer. What hidden complexities, what stories of managed uncertainty will you see now?